In our previous lesson, we were looking at the predictability of uniform acceleration to extrapolate more information about an object's motion. We mentioned that acceleration is influenced by forces. More specifically, it's a force that causes an object to accelerate. And so it's natural for us to say that a constant force would result in a constant acceleration. There's one situation in which an object would be able to experience a constant force and therefore uniformly accelerate. When it's falling. When an apple falls, it gains speed, accelerating in the downward direction. What would cause it to do that? Yeah, it's the force of gravity. The force of gravity from the earth pulls the apple downward. Since the force of gravity between the earth and the apple is constant as it falls, so is the apple's acceleration. So an object that is falling as a result of gravity would have constant acceleration. But wait, what if a cat leaps in the way and knocks the apple as it's falling? Would acceleration still be constant? Well, no. An additional force would influence the acceleration of an object. That's exactly why a person can jump out of an airplane and slow down with a parachute. A parachute really isn't a complicated machine. All it does is increase the effects of air resistance on the person. So it seems air resistance is but another force that would affect the otherwise uniform acceleration of a falling object. How significant is this effect of air resistance? Well, it depends on a number of factors, from the shape and velocity of the object to the density of the air it's falling through. Generally speaking, a more smoothly curved object moving at slower speeds through less dense air would have less air resistance. So, to amend our previous statement, an object that is falling as a result of gravity only would have constant acceleration. We called this specific condition of motion free fall, and objects in free fall experience uniform acceleration. Great. What would that acceleration be? Would it be different for different objects? Our intuition leads us to believe that objects with more mass would accelerate more quickly as it falls. That would explain why a leaf would fall more slowly than a rock, right? Actually, no. While our intuition usually provides us with pretty good insights in physics, we have to acknowledge the limitations of our intuition. Our intuition is based on our experiences, and our experiences are on Earth, surrounded by air. Don't feel too bad. Aristotle was wrong about this too. It was actually Galileo Galilei who famously helped us come to this understanding. As the story goes, Galileo climbed to the top of the Leaning Tower of Pisa and dropped two spheres of different mass to show that the gravitational acceleration was independent of mass. While there are many versions of the story, there's really no record of Galileo performing this experiment at the top of the Tower of Pisa. His experiments on motion do, however, show that the lighter object actually surpasses the heavier object in speed before the heavier object overtakes the lighter one in speed. But only by a small amount. That was enough to cause Galileo to question the ideas of Aristotle. And he was right to do so. Flash forward in time to the invention of the vacuum. No, not your household vacuum that keeps your floors clean. In physics, when we refer to a vacuum, we're referring to an environment without air, kind of like outer space. Now, we know that air resistance affects the rate at which objects fall, and that air resistance depends on the properties of the objects falling and the air. So, to determine if gravitational acceleration is truly independent of mass, we can conduct this experiment in a vacuum where air resistance has no effect, because there is no air. Okay, let's get our vacuum set up. Let's suck out all of the air. Let's give our experimenters some air-breathing equipment first. All right, continuing with our vacuum preparation. Now let's drop the two spheres with different masses. Actually, let's make it more dramatic. Let's drop a bowling ball and a feather so we can really see the difference. Ready? Set? Go! They hit the ground at the same time. The two falling objects experience the same uniform acceleration as a result of gravity, regardless of its mass. In fact, we were able to measure the magnitude of this gravitational acceleration on Earth to be 9.8 meters per second per second. Of course, this value would be different on a different planet. Now, to be clear, an acceleration of 9.8 meters per second means that every second a free-falling object would be gaining 9.8 meters per second in speed. So, if a crow drops a pebble from rest off a cliffside, the pebble's initial velocity would be 0. 1 second later, it would be 9.8 meters per second. 2 seconds later, it would be 19.6 meters per second. 3 seconds later, it would be 29.4 meters per second, and so on. Since this is such a special value for acceleration, we actually give it a symbol of its own. Gravitational acceleration is lowercase g. Yes, with so few letters in our alphabet and so many variables to represent, we end up using both lowercase and uppercase symbols for different things, which means lowercase g and uppercase G are not the same thing. Great, let's just sum up what we know so far. Objects in freefall have uniform acceleration with the magnitude of lowercase g, 9.8 meters per second in the downward direction, because objects in freefall experience only the effects of gravity, which means the effects of any other force, such as from a cat or air resistance, is 0, or at least close to 0. Oh, and because this motion is uniform, we can use those uniformly accelerated motion equations we learned about in our previous video. Perfect! Let's put this to use. A squirrel enjoying an acorn for a snack gets startled and suddenly releases the acorn from his grasp. Falling from rest, the acorn falls for 0.7 seconds before it reaches the ground. Assuming the effects of air resistance are negligible, what is the acorn's speed just before it hits the ground? Right, it's easy to tell this is a freefall problem. I mean, the video is named freefall. But let's ignore that small detail. What aspects of this situation fit a freefall problem? It doesn't have to do with the specific values of initial velocity or time. Instead, it has everything to do with the fact that the object is falling and it's implied no other forces are acting on it except the force of gravity. Since this is a freefall problem, we can use our UAM equations, where we know the acceleration will be 9.8 meters per second. Like before, we're going to pick out the variables in the problem. We know our acceleration is 9.8 meters per second. Falling from rest indicates an initial value of 0 meters per second. 0.7 seconds indicates a time. And the question, what is the acorn's speed just before it hits the ground, indicates a velocity after 0.7 seconds has passed. This is our unknown. Now we can pick an equation that has this set of 4 unique variables. Final velocity equals initial velocity plus acceleration times time. Substituting in our values, we find that the final velocity is 6.86 meters per second in the downward direction. So it's not really that different from the problems in our previous lesson. The only difference here is that these are free-falling objects with the specific value for acceleration. Oh, and don't be fooled by the term free fall. An object doesn't necessarily have to be falling down to feel the effects of gravity alone. Objects that are falling up can also be in free fall. Let's say our crow flings a pebble into the air. The pebble would accelerate as the crow's beak launches it upwards. But as soon as the pebble leaves the crow's beak, only the force of gravity would influence its motion. Assuming, of course, air resistance is negligible. The pebble, as it leaves the beak, would start with some kind of initial velocity in the upward direction. Let's say this is a super powerful crow and it launches the pebble with an initial speed of 29.4 meters per second. The pebble's acceleration would be 9.8 meters per second in the downward direction. Since the acceleration and velocity are in opposite directions, it's no surprise this pebble will lose speed. In fact, 1 second later, the pebble's velocity would be 29.4 meters per second minus 9.8 meters per second, or 19.6 meters per second. 2 seconds later, the pebble will lose another 9.8 and its new velocity will be 9.8 meters per second. And 3 seconds later, it will reach 0 meters per second. Yes, eventually an object falling up would reach a speed of 0 meters per second, and for a moment it would be still, before changing direction and once again fall back down. Right here, it's clear why we use positive and negative values to indicate opposite directions. Imagine you're on a number line. These numbers represent your velocity. If you start with the positive velocity, you'd be starting on the positive side of the number line to the right of 0. If you're an object free falling on its way up, you would lose speed at a rate of 9.8 meters per second. Let's call that about 10 in the opposite direction. As long as you're moving, you'd eventually reach 0, just like the pebble eventually reaches a speed of 0 at the peak of its motion, and start entering the negative region of the number line, just like the pebble would change direction and start falling downwards. As you continue into the negative region, your magnitude or absolute value would grow, as the pebble would gain speed on the way down. The entire time the pebble is in the air, the object is accelerating at the same value, 9.8 meters per second. On the way up, the acceleration is opposite to the direction of motion, causing it to slow down to a stop. But on the way down, the acceleration is in the same direction of motion, causing it to gain speed. If the pebble reaches the same position from which it started, the pebble would have traveled the same distance up and down. It would have lost the same amount of speed on the way up as it gained on the way down. And ultimately, its speeds would be the same at the same heights. And finally, it would have spent the same amount of time traveling upwards as it does traveling downwards. So we say that this upwards and downwards motion of free fall are completely symmetrical. Great. So the situation of free fall doesn't just apply to objects falling down, it applies to objects that are also falling up as a result of gravity alone. The uniform acceleration is 9.8 meters per second downwards the entire time, regardless if it's moving up or moving down. And since acceleration is constant the whole time, the upwards and downwards motion are completely symmetrical, which tells us that the falling object takes the same amount of time to travel up as it does to travel down, and has the same speeds at the same heights along the way. Awesome. Let's just do one example to make use of this information. A seal is bouncing a ball up and down off its nose. As the seal knocks the ball up, it gives it an initial speed of 3 meters per second. Assuming air resistance is negligible, how high does the ball get and how much time does it take for the ball to fall back down to the seal's nose? Okay, it's really 2 problems built into one. I thought I could sneak that one by you. So, let's gather the information we have. Since we're dealing with a free-falling object, we know the acceleration is 9.8 meters per second downwards. The initial speed is 3 meters per second upwards. Let's just make sure we have opposite signs here. And the question, how high, indicates a displacement, the unknown. Wait, that's only 3 variables. We know that each of our UAM equations has 4 variables. Are we missing something? Well, there's actually some hidden information in this problem. The fact that the ball is in free fall doesn't just mean the acceleration is 9.8 meters per second. There's more that's predictable about this motion. Like, for instance, that the speed at the highest displacement is 0 meters per second, and that the velocity just before it reaches the seal's nose again is 3 meters per second downwards. Since we're looking for how high the ball gets, we can set the final velocity to be 0 meters per second. Remember, the variables are connected, right? It wouldn't make sense for us to use the final velocity of 3 meters per second downwards because that's not the velocity of the ball when it's at the displacement in question. Now, we have 4 variables, one of which is unknown. With this set of variables, we can use the equation final velocity squared equals initial velocity squared plus 2 times our acceleration times our displacement. Since we're solving for displacement, let's isolate delta x. We can substitute our known values, and our displacement comes out to be 0.46 meters. Excellent. Now for the second part of our one example. How much time does it take for the ball to fall back down to the seal's nose? Let's recap our information given. Acceleration is 9.8 meters per second downwards. Initial velocity is 3 meters per second upwards, and time is unknown. We also know that the velocity at the peak height is 0 meters per second. The velocity when the ball reaches the seal's nose again is 3 meters per second downwards, and the maximum displacement of the ball is 0.46 meters. We're looking for the time it takes for the ball to go up and down. So which piece of information do you think is useful to us? Actually, all of them. Let's say that we use the final velocity of 3 meters per second downwards. Since we're looking for the time it takes for the ball to travel from the seal's nose to the seal's nose, using the final velocity of 3 meters per second downwards would give us the time we want. However, we can still use the other values to calculate time. Of course, if we use the velocity at peak height, or if we use the maximum displacement, then the time we would get is really just the time to travel upwards. That's not a problem though, because thankfully this kind of freefall motion is symmetrical. So the time up would equal the time down. We would just need to double the value for time. No matter your method, you just need to be cautious about the direction of your vectors and therefore the sign of your vector numbers. And be cautious about the connection between the variables. There you have it. We've learned about the special condition of free fall as a type of uniformly accelerated motion due to the effects of gravity alone. With that, we've learned the features of this motion that make it predictable and applicable to the use of our uniformly accelerated motion equations. In our next lesson, we'll look at another special case of motion, projectiles. See you later on Penguin Physics.